here we are just share the link for feedback of session number 1. So simultaneously, please fill that feedback form. It is requested to all of you, kindly fill the feedback form. Because it is a mandatory requirement as per the AICTE format. हाँ, hello, Mr. Kalpak Iyer. Are you able to hear me, sir?
Hello, sir. Good
Hello,
evening.
very good evening, sir.
I hope I am audible and visible to you.
Yes, sir. Yes, sir. Now you are visible. Audible was well before also.
Okay.
Okay. Good, very good evening, sir.
Very good evening to you, sir, and everyone
So,
available here. Yeah.
okay, so before I hand over the session to you, let me just introduce the Kalpak Iyer, sir. Dear participant, Kalpak Iyer, sir, is the CEO of Tequity Engineering Private Limited, a Mumbai-based startup working in the field of lab-scale advanced manufacturing technology. He has completed his bachelor's in mechanical engineering from College of Engineering Pune in 2009 and master's in business administration for GIM Goa. He spent a significant time as an employee in a Micro Tools Private Limited, Singapore-based company. Most of academicians know about this company, and later on he has started his own startup with Tequity Engineering. Now it is a 4-year-old business, and their aim is to make the advanced manufacturing technology based, affordable, accessible, and high quality machine tools. They are coming presently. This firm is associated to manufacture like CNC micromilling centers, SPD 3D printers, and filament extruder for FDM, etc. So, with this short, very brief introduction, I request to Kalpak Iyer, sir, please start your session and we wish all the best to you also, sir. Over to the Kalpak, sir.
Thank you very much, Professor, sir. Thank you so much for that warm introduction. I hope my screen is visible. I've shared a presentation.
Yes, sir.
Okay. So today my talk will be covering two different topics. The first one will be on machining technology, a machine tool perspective. And the other one will be slightly different, but very interesting technology that we have developed, which is called selective powder deposition 3D printing, a technology to 3D print metals, sand, molds, and glass. So thank you very much for this opportunity. I will just share a little bit about my company. But before that, you have to pardon me if I stutter a bit. My nervousness might be apparent to some of you. I am not used to being on this side. I'm usually in the audience side, listening to all the brilliant faculty here. So you have to pardon my ignorance if at all sometimes I say something which is not fully accurate. At the same time, it is a terrible situation for me to follow such a brilliant lecture by Professor Harshit Dave, who also happens to be a mentor of mine, a very, very avid supporter of what we do. And I owe a lot of our achievements and our ambitions to people like Professor Harshit Dave, who have kept the spirit of innovation and also the spirit of sticking on to your ambition. So with that, I'll start my talk. So about my company, I started this company post the pandemic, and the idea was that I had spent about 7 or 8 years in the field of machine in the machine tool area, especially working in the field of precision and ultra precision manufacturing. So the company in question was Microtools. I was heading the India business for that company. Some of you may have interacted with me in the past, and we took a lot of learnings from there, and we also developed our own micro machining setup, focused to micro milling, and that machine is something that we are already deployed in at many places, including industries. Another product that we work with is filament extruders, which is the filaments for additive manufacturing, and our own machine that is the Aero 3D selective powder deposition, which is jointly developed with Aero 3D USA. We are the Indian manufacturers for this technology, and basically we supply all over the world. And it's a very interesting additive manufacturing technology. So with that, I will start my talk. I will try to split my talk into two halves. The first one would be a talk on hybrid micro machining, a machine tool perspective. It shall basically cover what is micro machining, the three M's of micro machining, what makes a machine tool capable. If you wanted to develop a machine tool, what are the key things you have to keep in mind? Why hybrid micro machining? What is so special about it? We will look at a case study. And also, if you want to machine something, if you want to build a part through micro machining, depending on what the part is made of, what machining process you must choose. I will try and cover all of these things based on my experience. The second part of my talk shall be on SPD 3D printing. It's a novel additive manufacturing technique which is developed by us. I will talk on how this technology works, what all materials we can print, the parameters for those, the machines available, and the research areas and targets. So that's how I shall structure it. What we can do, if your permission is there, is we can split the talk in two. We can have a question answer session after the hybrid micro machining section and one more after the SPD 3D printing section, if that is okay. Because I understand there are two different technologies. So firstly, I think Harshit sir covered this really well. What is micro machining? Uh, I'll just share some photos of some nice parts, something that we use on a day-to-day basis. A ballpoint pens. The ball itself is micro machine. It's amazing that such a thing can be 5 rupees or 10 rupees. Sometimes it's tough to believe. Surgical needles. I hope we don't use this a lot. But yeah, now even smaller needles are out in the market, but they typically are between 0.35 to 0.75 mm. Then human hair, some of us have a lot of it, some of us are losing it. Uh, but all of us have different diameters of human hair, and tends to be between 70 microns to 180 microns. Harshit sir had a very good explainer of what is a MEMS device. So MEMS device they tend to be in the tens of microns range. So as you can see, I'm going from larger to smaller. And then if we really talk about things around us, nature is the best creator, definitely. And red blood cells are 5 to 10 microns. So that doesn't mean that we cannot make something that small. We can also manufacture nano, but what nature can do, it's virtually impossible to replicate. There are plenty of areas of micro manufacturing, and my talk shall actually show a lot of images of parts that I have myself been part of making. And it's very exciting to be a part of this field, actually. So these are all the areas that we have actively worked in. and aerospace, mold making, medical sectors, optoelectronics, microelectronics, and of course research and training and prototyping. A lot of areas and a lot of everyday products that we use have tons of micro machining in them, and nano machining in them. So let's talk about what makes a good micro machining system. So as my talk will focus on machines, as we are machine makers, uh, I may not be able to answer very well fundamental questions, although I have a fair understanding, I hope. But I will talk about the machine tool perspective. There are three things that go into making a very good high precision machining system: the machine tool itself, the machining process that you employ, and measurement. These three are very crucial, especially if you want to achieve high precision micro machining. Let's look at each of them briefly. The machine tool itself. Now I have to give credit here to Microtool Singapore. I will be giving illustrations on micro machining through one of their machines, DT110, which is, in my opinion, one of the most capable, versatile micro machine tools in the world. And it was created by Microtools Private Limited, Singapore-based company. No intention to market the company here. The idea is that let's take examples from some really good uh, industry proven techniques, and let's try to learn them, deconstruct them, something like that. So as you can see, a schematic of the machine is in front of us. Uh, the whole thing happens on a granite bed, a monolithic granite base. You can see in blue bellows, the y-axis is on the mounted on the granite base. There is a stiff, typically cast iron gantry, okay, that is at the back of the granite bed, again stiffly mounted. The x-axis is mounted on the gantry. The z-axis in turn is mounted on the x-axis, and then you've got a tool head or a spindle mounted on the z-axis. Now let's see what all is there at the base on the y-axis, that is, or we can call it the table. We have a microscope or an optical device for measurements. We have a cutting tool post, and we have also a tank in which we can do electrical discharge machining or electrochemical machining. Of course, the tool head can be swapped for different types of tools, as we will see sometime later in this presentation. The idea being that we need to have a very stiff, low vibration, rigid, and high precision structure for us to be able to do micro machining. If any of these are not in place, it is very difficult to uh, achieve high precision micro machining. So some of the broad characteristics on what are required for the machine tool. Firstly is the drive contact mechanism, whether you can go for mechanical, aerostatic, or hydrostatic driveways. Motors that you select. So broadly, micro machining tools use stepper motors, AC servo motors, or linear motors. Each have their own benefits. Real-time error compensation. So basically, a lot of micro machining can be open loop. Then you're actually at the mercy of hope and nature, because over time wear will happen on your guides, on your drives, and you will not be able to compensate for them. A closed loop system usually is much better because it will give you real-time error compensation. And as you can imagine, even a 20 micron error can actually completely derail your part, because sometimes your parts are itself 50 microns or below. The encoder itself, the resolution of the encoder is very important. So the encoder is the device that will be able to read the position. Okay, so it is preferred to have laser interferometry here. So optical scales are better to be used, and also rotary scales. Some very good rotary encoders are there in the market. So which encoders that you use? That is, of course, if you're going for a closed loop system. The machine accuracy and repeatability. Now, all of it boils down to this: if your machine is accurate but not repeatable, or if your machine is repeatable but not accurate, in the long term, it is difficult to achieve micro machine parts of high quality. System rigidity. No brainer. All CNC machines tend to require very high rigidity for obvious reasons. A very important factor is dampening and damping provisions, whether you have active or passive dampening systems. Harshit sir also mentioned very well about this point. The vibration that or the chatter that is caused, especially in tool-based machining, can have a massive impact, especially when we are talking about sub 100 micron or sub 200 micron features, because the chatter itself can cause parts to break, tools tools to break, and tools are very expensive. And finally, the vibration isolation. So something like the nut, the friction of the ball nut with the ball screw also causes vibration. It's not just that the tool and workpiece cause vibration. Your cooling fan also causes vibration. Your coolant pump also causes vibration. Uh, you are standing on the ground also causes vibration. The machine next to you, that is also causing vibration. So how much isolation can you achieve, and how much isolation do you need to achieve, are all the perspectives that you need to look at from a machine tool standpoint. The machining process. Okay, this is the second M. So broadly, there are two types of machining process: a tool-based and a non-tool based process. So what process do you want to select? The tool itself that you're going to employ. So if you're going to use a tool-based process, that what type of cutter or what type of tool will it be? So in case of grinding, say for example, what type of grinding media or grinding tool we will be using, if it's turning or milling or drilling, what is the material, whether you want to use PCD, single crystal diamonds, whether it's carbide, sometimes high-speed steels. And in the case of non-tool based machining, say electrical discharge machining, electrochemical machining, laser machining, what are the different parameters you need to study? Then it is very important, and we will see in the later part of this presentation, why hybrid manufacturing in micro machining is especially important. Uh, I will not elaborate here much. Then fixturing and tool workpiece centering. As you can imagine, uh, your fixturing of the tool is of critical importance, and then relating the tool center to the workpiece center is another very important aspect. Handling. If you're talking about fixturing a 100 micron milling cutter with a shank of 2 mm, you better be sure that you're not going to touch the cutting tool. Another thing, if you have a diamond turning tool, single crystal diamond of nose radius of 50 nanometers, sorry, 50 micrometers, better be sure that you're not going to touch the edge. How do you handle it? And refixturing. So sometimes you need to uh, refixture your part, and you need to have very good fixturing mechanisms to be able to locate your part again. So these are the uh, aspects of machining process. And finally, the aspects of measurement. So it is preferred to have on-machine measurement in when we are trying to do micro machining. You need to, as much as possible, reduce manual intervention, reduce manual intervention and handling. You need to reduce refixturing as well. So that is where the number of axes on your machine will actually help. In the case of reducing handling, the versatility of your machine, say for example, the same spindle can do milling and then it can start doing EDM. That will reduce handling. Real-time measurement and viewing can be very important in tool-based processes, especially optical measurement and sensor-based measurements for different types of sensing are the criteria that one needs to consider when creating a micro machining center. So these three things, the machine tool, the machining processes, and the measurement systems are all the ingredients to make a good micro machining center. And one has to choose which one they need to uh, prefer and go for. As you can imagine, the choice is always limited by cost. You can want a very precise machine, but the cost start going up, and not just cost, skill. So it's not just simply that I can buy components and sit and assemble them. There is a lot of skill involved in making these machines. A very good example is the DT110 machine that I spoke about. The single same machine can do these following processes. So the ones in red are tool-based processes: micro turning, milling, drilling, and grinding. The ones in orange are electrothermal processes: micro EDM, micro wire EDM, and micro wire EDG. and this is laser machining. So all of these processes on the same machine, and we will see what makes it so capable and why there is value of having all of these processes on the same machine. The machine is basically a 3-axis machine. It would be better if it was a 5-axis or a 7-axis machine, but you can't always get everything. It has closed loop continuous control. It has on machine measurement through an optical microscope. It has a fairly decent positional accuracy of 1 micron per 100 mm. Machines that were even 8 to 10 years old displayed a very, very tight accuracy. Resolution of 100 nanometers. So resolution is the basically the least value that the machine can read and travel. Uh, it has an electrically isolated spindle. What this means is that the same spindle can at one time be doing milling, for example, and at the switch of a button, it can switch to an EDM head, and it can then start doing EDM. And it has a spark control mechanism. So I will just be keeping my talk with the focus on this machine, but we will be talking about different types of micro machining. So continuing on what makes a capable micro machining center. The idea is to share this information is so that it serves as a guide for somebody who wants to develop their own machine and maybe wants to get some good pointers on how to start. So what makes a capable micro machining center? So the basic specs, the travel. Okay, so how much travel do you need? So typically 50 mm to 200 mm is the travel for each of the axes. Good enough for micro machining, but sometimes larger machines are required. For example, large dies and molds require very small holes at select locations. The machine has to be built with consideration of maximum vibration isolation, stiffness, accuracy, and corrosion resistance. Very important aspects for developing a good machine. The accuracy and repeatability both should be better than 5 micron per 100 mm of travel. I think it kind of goes without saying, and I think we all can appreciate why that is the case. And gantry structures are good structures for these types of machines. Again, gantry structures provide the best rigidity and very high stiffness compared to many other structures. There are less overhangs here. Uh, Isolation, vibration isolation, you can have a passive isolation. So passive isolation is basically dependent on the materials you select. For example, you use a monolithic granite base or a ceramic base. You use cast iron components, which also aid in damping. Also, you use some passive damping pads below the granite base so that all vibration can be absorbed by the machine. Alternatively, you also have active vibration isolation systems, which are basically hydraulically or pneumatically controlled, and they usually sit on the base of the granite table, and they are constantly able to eat a lot of the vibration, but they're quite expensive. And the machine base itself, which I said there are many materials to choose from, and the machine size. So you can have a tabletop structure or a standalone machine. Tabletop machines are quite good enough for micro machining actually. They do a great job. You don't need to have a very large machine. Then the motion, very crucial for any CNC machine. What type of motion you choose. Typically LM guideways, they must have high rigidity, accuracy, reliability, and smooth motion. When you want all of these things, it is a little expensive to choose the right one. Because it must also be able to withstand even the smallest radial loads and moment loads that the machine can generate. So now micro machining system will not generate anywhere near the radial or moment loads or the axial loads that the large machine will generate. But even those small loads have a lot of impact on the quality of the parts. The slide stiffness is a very, very important aspect because if it is not stiff, basically, especially on dynamic load conditions, you have very unreliable results of part finish, of part dimensions, etc. Then the drive that you choose, lead screws also work. Lead screws have a bad name, but lead screws can be very well made and they can work. Ball screws are better, lower friction, but linear screws are the best and the most expensive. Very rarely does it happen that the best is not the most expensive. So it is the case here as well. Same with motors. You can use stepper motors. stepper motors are very strong, quite accurate, but they have very bad, much inferior jerk control systems. They cannot get to their top speed as fast as something like servo motors. But again, here the best in class is the linear motor, definitely. Uh, what is a good machine without good CNC control? Well, a lot of old machines have very, very high accuracy without CNC. Sometimes when you go, especially to many of your institutes where you must be teaching, some of the old machines will baffle you, and some of the components that those machines have, I wonder how people in the 60s, 50s built these machines, because that was the true era of mechanical engineering. All systems, actuations were mechanically made. Now we have a lot of convenience with really, really powerful controllers, which help us do a lot of the hard work. But yeah, I mean, I'm still nostalgic about having a good mechanical design, cam and rockers doing a lot of the heavy lifting. But good controllers can be open architecture, closed architecture. Popular brands are Siemens, Fanuc, Omron, and open brands. There are many of the good brands available. The resolution of the machine, you want high resolution. So at least have a 1 micron or 2 micron resolution and go down to 10 nanometers if possible. Feedback. So here is a good question whether we want open loop or closed loop feedback. If you need closed loop feedback, you need an encoder. But encoders also have their own errors. So you need to have a very expensive encoder, very good encoder, preferably glass with laser interferometry to have good feedback. And then only you can expect reliable compensation. I personally have tried cheap encoders for closed loop, and I thought that it's better to have an open loop system without all the fuss. It's cheaper to do that. But if you're going for a closed loop feedback system, have a good encoder. Uh, the next one is the HMI, human machine interface, uh, and operational skill intensity. Of course, it all boils down to the spindle head. The micro machining, you want high RPMs, um, upwards of 20,000 if possible, upwards of 50,000 is better. Then there are some considerations of the runouts of the spindle, radial and axial runouts, what kind of uh, torque or what kind of power output they have. And also, because we're talking about hybrid micro manufacturing, we should have switchability of tool heads. It's a very useful feature in micro manufacturing, as some of my examples will show you. Good to have a good measurement system on board if possible. Uh, and some accessories. So I told you that this, giving the example of this machine, there are these accessories that you have: wire EDM, wire EDG, laser head, high speed spindle, and ECM device. So the case study that I promised you. The objective was to make a well finished 40 micron hole on a stainless steel plate. So how do you do that? So the approach idea was that let us turn the shaft to a 35 micron diameter. We'll measure that electrode. Okay, that shaft becomes the electrode, because I told you the spindle, after turning, micro turning, can actually be made into a EDM spindle, and then it can actually EDM dicing the hole. So this is as simple as that. What is so difficult, right? Let's make a 35 micron diameter shaft, measure it, and EDM dicing the holes. Quite straightforward. Not really. Okay, so you start with micro turning, which is done with the aid of the measurement system. You need to be able to center the tool with regard to the workpiece. The workpiece is usually mounted, in this case, on the shaft, so it's vertically mounted. The tool is on the bed, the single point cutting tool. This is a PCD tool that was used, polycrystalline diamond. Uh, Harshit sir said very aptly that up to 100 micron micro turning worked quite well, but after 100 micron, so we let me start that a brass workpiece was selected, and then micro turn up to 100 micron. No worries, the machine is so well built, it did it, and you were able to see it live, happening live. You can see the image here, and then we tried to go below, and this starts happening, deflection, and it's quite irritating that this deflecting. So is it because your uh, material that you bought, the vendor is cheating you, or maybe the tool is not good enough? or whether the machine is not stiff, you start doubting yourself a lot, especially when you do these kind of machining technologies. Well, it starts to become apparent that the nose radius of the cutting tool used usually is 200 microns, 150 micron nose radii. So the nose radius, instead of becoming a cutting agent, also it always adds a radial force. Okay, if this is my shaft, there is a radial element to the um, cutting aspect of turning, and majorly we want axial shear, but there is a resultant force. Now a big stock is easily able to withstand and it does not deflect, but when you start talking about sub 100 microns, deflection becomes a real problem. So why don't we have a tool with a smaller nose radius? Well, because it's not easily available or it's extremely expensive. And there is a reason why we have a nose radius to cutting tools. I will not go into why. We all know why. So what do? We cannot start with a very small nose radius tool because we know that it will chip off and it will be useless. So the idea was, hey, let us do one thing. Let us machine up to 100 micron through turning. Then, because our machine the spindle has the capability of doing EDM, let us switch on the EDM and let us do wire electrical discharge grinding. It is an EDM process. And long story short, this nose radius became this. So the nose radius was turned down to 5 micron. So it's almost a sharp edge. Okay, 5 micron nose radius. In wire EDM, the wire has a positive is the anode, positive polarity, and the polycrystalline diamond has a negative polarity. Polycrystallized diamond can be EDM machined because it is usually sintered with cobalt or some other sintering binding agent. So it was machined on the same setup. So basically, we turned up to 100 micron. We took that turned shaft, put it in the EDM tank. We made the spindle into an EDM head. We used wire EDG to basically make this smaller tool. We switched off the EDM. We bought the tool. We bought the workpiece back to the uh, station, and now we attached a new tool with this small nose radius. And you know what? It kind of worked. We are able to make micro shafts. How small? Well, here is an image of a shaft of 11 microns on the top right, and on the bottom right is human hair for comparison. As you can see on the leftmost photo, the whole thing is first turned. The leftmost boundary, you can see micro turning, and then that turn shaft is further chiseled down through further turning from a very small nose radius turning single point cutting tool and achieved 11 microns. And when this was made, this was the smallest hole made through EDM process of 6.5 microns. So that turning insert or turning tool or the turned electrode was further turned to 5 microns. And then a 6.5 micron hole was made on stainless steel. And quite interesting that it was possible to do this. So now at the business end of the presentation, some of the micro machining processes, some images of a lot of the images of parts we've made in actually in India at different places over the years. So these are some EDM electrodes. This is again not made in India. It's a surgical pin uh, made in Singapore. This is the shaft that I showed you. Then some motor shafts that we actually, some of our clients made. Micro milling is a very interesting operation. Most of the images here are made here. This is a biomedical surface uh, textured on titanium alloy using a 100 micron ball mill, dimple structures. Again, this is a blood diagnostic kit. A lot of the work here happened at IIT Bombay. Then you've got square pillars for some heat applications. Again, a heat sink here, which is like a shape like an impeller type of a shape. This is a very challenging part that we did at with IISc Bangalore, where this is SS316L, and we made these pillars. And you can see that the base of the pillar is about 350 microns, and the top had to be 40 microns. So very difficult to achieve this without breaking the pillar. This was done through milling. successfully at that. So micro grinding. Okay, so it is not really conceivable to put a glass workpiece on a machine and get on with it. You know what is going to happen? It's going to shatter. So you need to be careful about how you handle glass or other brittle materials, and you need to get a lot of the parameters, especially the tool speed, the tool type. Here we use some kind of PCD or CBN grinding heads or some other abrasive media, and we give very light depths of cut. We have a very narrow range of the depth, and we are able to do micro grinding successfully. A lot of work on this has happened at IIT Patna. Very good work on the micro grinding on glass. Micro EDM. So another very useful process, very widely used in a lot of areas. The most widely used area in India, I would say, is the tool rooms, which use micro EDM a lot for different applications of tools and dies. But here on the left, you can see some reverse EDM machined tools. I can get into it later if interested. Then some 120 micron channels. These are 200 micron by 600 micron arrays. And this part we made for ISRO. It is a bush with highly accurate non-radial holes using micro EDM. Similarly, micro wire EDM, we all know what wire EDM is. So micro wire EDM usually uses very fine wires. Uh, if I remember correctly, 20 microns is the smallest wire that we use. I might be wrong. It's maybe 30 microns. Maybe 20 or 30 microns. Here you can see two slots, and the wall between the slots is 2.5 microns. It's very small. Again, this is through EDM, wire EDM, and some micro fins made, micro gears made, so micro wire EDM. Wire EDG, which I told you during the example of the micro turning example. Wire EDG is a very interesting process. So even some of the micro grinding tools are made in situ on the machine using wire EDG process. These up to 5 microns electrodes can be machined. Of course, for electrical discharge grinding or machining, the tool has to be of electrically conductive material. And well, last but not the least, at least in my presentation on this, is laser machining. Very fast, very expensive, but very useful process for micro machining. A lot of the other processes are slow, uh, very intensive, but this is very good for 2D machining or making some holes. Here on the right top, you can see a part that it was a trial we were doing with DRDO of a spin actuator for triggering missile systems. This is a micro heater made out of nitinol or shape memory alloy for an aerospace application. These are just some silicon blocks that we machined, and some micro cavities for the micro needles were machined using micro laser machining. Okay. Finally, I think this is the last slide, yeah, on this subject. Which process to choose? Okay, so there are more processes, right? By no means have I comprehensively mentioned the processes for micro manufacturing, but these are quite a lot of the processes. And as you can see, if you're able to combine the machining process and the measurement systems well, micro machining is really possible. And as a manufacturer of small machine tools, we make micro milling machines at a very affordable price. Of course, you have to make compromises when it comes to these tools. And the idea why I chose to make these machines is because the presentation I gave is a very expensive machine tool, and not many industries can really adopt it. The idea was that, hey, I don't want 100% of the capabilities. Why not 80% of the capabilities at a very lower price? So put a lot of those learnings into action, and hopefully we are able to do something good with it. Now, as you can see, some of the attributes that you want to have. 1 second, can I just close this? Yeah. Some of the attributes that you want to have are material removal rate, complexity, hard materials, brittle materials, surface finish, aspect ratios, and scale. 1 to 5, these are all rated from 1 to 5. 5 meaning that the process is very good at it, and one meaning that the process might not be very adept at it, or it might be slow, whatever it is. So let's take an example for, say, micro grinding. Very slow material removal rate. You can't do too many complex stuff with it, but you can machine really hard materials. You can machine brittle materials. As you can see, this is the only process that scores a 5 in brittle materials, right? It gives great surface finish. You can't really expect a lot of aspect ratios, and you can have a decent micro machining with it. So each process has its own pro and con. It can approach a different material, because the first part of the presentation was about the machine tool, but then at the end of the day, what do you want to machine? And based on that, you choose your process, you go about fixturing it, you set your experiment or you set your process, and then you try and achieve your part. So that was my talk on micro machining. And I think if um, any questions are there, I would like to address them now before I continue on to the other talk on selective powder deposition.
Participant, is there any question?
I hope the presentation was visible and I'm audible throughout, sir. Okay. So I'll
Hello.
start with, yeah, yes,
Hello,
sir. There
Kalpak
are,
sir. In
yes,
message box,
I'm
some of
seeing
the
it.
participant asked a certain questions.
I'm seeing that, sir. I'm seeing that. Shubhangi ma'am has asked which software tools are used in micro machining machine video. Okay, I shall share a machine video link later on. Is that okay? Uh, I can definitely show software tools in used in micro machining. Well, uh, I don't exactly know which software you're talking about. If you're talking about the HMI human machine interface, most companies design their own softwares. Then there are some other aspects in micro machining, especially CAM. You need to have a very good CAM, especially if you're doing some complex parts. Uh, Master CAM or Solid CAM or some other softwares also can do some really good work. Uh, and I am not sure which other, oh, user friendly software for what regard. You can text. In the meantime, I can try and address Dr. Sanjeev sir's question. Which process is most suitable for cutting tool texturing? Okay, good question, sir. Depends on what the cutting tool is made of. First, try to laser texture it. So lasers are an inexpensive way to basically texture the a lot of the materials. So metals can be textured, polymers can be textured, um, even ceramics can be textured. So it depends on what type of texturing. So if the laser does not work out, try to use a ball mill. And if you want a deterministic texture, ball milling is great. If that also doesn't work, if the laser is not working for you, the ball mill is not working for you, then you need to go into maybe grinding. Okay, so grinding is very difficult for very deterministic textures, but you can actually at the end of the day try grinding. That's how I would approach the problem. But again, you can really choose the process based on the material. At the end of the day, different materials will respond to different processes. Whether coolants required, very good question, Venkatraman sir. Uh, Very rarely, because we are removing a very less, a small amount of material. Coolants are typically not required in micro milling, but occasionally required, especially if you are working with certain materials like titanium alloys. They tend to heat up a lot. So if you're the major concern here is tool wear, because the material under question is heating up a lot. It reduces the tool life. So that can become an aspect, and you can require heating. In most other cases, for tool-based machining, coolants are not necessary. Air is good enough, but sometimes they can be necessary. For EDM, of course, you need to have a dielectric, which also acts as a coolant. but also dry or air EDM, because air also is a dielectric at the end of the day, can be used, but it is preferred to have submerged systems. So I hope that is that answers your question. Uh, what type of coolants? So actually, we can use all types of, like, so for example, the oil-based coolants, synthetic coolants are most commonly used for this type of thing. Uh, okay, for GUI software, Shubhangi ma'am, uh, most of the companies develop their own GUI softwares uh, because they want to have their own things. But there are a lot of open source GUI software. So you can go onto GitHub. You can check out this open source called Open Builds. So Open Builds has a wonderful GUI. In fact, we use it for our own machine. We don't want to be developing GUIs. We're not good at that. So you can actually check that out. Hitesh Mehta sir says, can you share? Of course, I'll share the PDF. Why not? We can do that. Uh, is there GUI software available for students? Yes, Shubhangi ma'am. I said open builds. Venkat Raman sir. Thank you so much, sir. I really hope you'll also enjoy the next session. Uh, I know many of you will be hungry, but Taylor sir, can I proceed with the SPD
Yes,
talk?
yes, sir. If there is
Okay.
a no question, then we can go for the second.
If there are questions, you can keep adding them. I will take them after my next talk. I
Okay,
believe a
sir.
lot of you might find the next talk very interesting because it's a new process developed very recently, and it is a low cost approach to achieving 3D printing, which is one of the very important techniques of today's generation. And once again, the idea being that we should be able to make our own technologies in our country and be able to solve some very important problems. So here is a presentation on selective powder deposition, or SPD. Okay, so SPD is an additive manufacturing process or a 3D printing process. I would like you to please correct me in the comments whether the right word to use is 3D printing or additive manufacturing, because I've been told different things at different places. So yeah, it's a two-stage process. First, you do the SPD 3D printing, and then there is a next stage which happens usually in a furnace or an oven. Um, it the idea is that gravity-based pouring happens in a crucible. So the whole thing happens in a crucible or a refractory kind of a container, and we are basically pouring certain materials inside the crucible. I'll explain through videos and through great illustrations how this process works, but just giving you an overview right now. So as I said, gravity-based pourings, we need to have pourers. So pourers have openings. There are different types of pourers that are used in these machines. Pourers have openings of 1 mm, 2 mm, 4 mm, or 10 mm, depending on the machine and the question. So what are we pouring? We are pouring two types of powders in a crucible: build powders and support powders. So build powders, by the name, as the name suggests, are actually the powders of the material that you want to print. But support powders are basically powders that support the build. So because I'm printing inside a crucible, if I only pour build powders, it will not fill the entire crucible. The whole structure will collapse. So support powders are the filler powders that fill all the places where there is no build powder. Please stay with me. The videos will explain it better if you don't understand it right now. How does this work? We have an STL file. We upload that file into the printer. We have our own slicer, developed our own slicer. It slices the part. So in a 3D printing process, an STL file or a CAD file, which is stored in the STL format, is uploaded onto the machine. The slicer basically slices this component into small slices. Many people will be aware of this, but I'm just explaining in case somebody doesn't know it. And then there is a G code generated for each layer, each slice. So that is the basic principle behind it. And based on the G code generated for each slice and the crucible diameter fed to the system, say for example, slice number 1 has a square that is of the build powder. It will pour the build powder in that square, and in that same layer, which is probably 0.5 mm thick, you pour a sand or a support powder. A video will explain it. Once this is done layer by layer by layer, you have basically a crucible filled with build and support powders. But again, there is no heat, there is no binder, there is no laser, nothing is happening. It's just deposited powders, very, very selectively deposited powders. If you invert it, all powders will flow out. So what we do is we carefully place it inside a furnace. And in the furnace, depending on what your build powder is, you can have infilling, sintering, or curing process. I'll come to each of these. And what are the end parts you can achieve? Cores, molds, or parts of metals, glass, depending on your configuration. Now, here's the interesting thing. The most 3D printing processes will only support one category of material, whether it be ceramics, metals, polymers. Am I missing something? Sands, composites, depending, right? So most of them will usually support only one of the type of materials. This process is kind of material agnostic. We can print metals, glass, and sand, shell sand in the same process. Just to show you some examples of 3D printed parts. On the left hand side, you can see a mold for casting. The mold is printed, single piece mold is printed on the SPD process. Okay, this is shell sand. Shell sand is basically sand with a resin coating. And when the resin coating is basically heated to about 150 to 200 degrees Celsius, it basically melts and it binds the sand together, forming a single mold. Shell molding is a very commonly used casting process. Many of you might know it. We are just exploiting that process, but in a 3D printing perspective. There's a shell mold. Of course, this goes to a foundry. You pour molten metal and you achieve your part. On the right-hand side top, you can see glass. I'm sure most of you have never heard of glass being 3D printed. Well, we can do that. And on the right bottom, you can see a piston, which is a metal piston made again using this process. The metal was itself printed using this process. Now, let me explain a little bit from this image. This is a Model C. It's a basic version of this printer. As you can see, there are 4 hoppers. Okay, and each hopper is connected to a pourer. You can see some things dangling here. There are 4 pourers. 2 of the hoppers and 2 of the pourers connected to it will have a support powder, and 2 of the hoppers and corresponding pourers will have a build powder. Support powders are usually refractory materials like silica sand, alumina sands, ceramic sands, etc. And the build powder is usually of the part that you want to print. For example, if you want to print a metal alloy, the build powder will be metal powder. If you want to print glass, the build powder will be glass. And if you want to print, say, a sand mold, the build powder will be an appropriately resin coated sand. So this is the basic aspect of the process. I will explain the process to you with the help of a video and this poorly made presentation animation. Please bear with me. So the light gray is the support powder and the dark gray is the build powder. So basically, this is a layer by layer process. The boundary you're seeing is the crucible, the front view and the top view. This is how it will look. Just an example illustration. Okay. And then you take it in a furnace, you do certain furnace activities, heat, depending on the process. I will explain each of the processes. And you are able to achieve an end part. Now let's actually look at the video and I will explain through this video what is happening. So this is the 3-axis CNC machine. That is actually a 3D printer. You can see a pourer. Okay. And pardon the amateur quality of the video. It is a very new process. This is the silica sand being poured. The reason why we're showing in a petri dish is so that you can see the process. You saw it went and parked the pourer, it went and fetched another pourer. Now this will park this pourer and fetch a build powder. Build powder is metal, is iron powder in this case. So the illustration is for a metal alloy part. So as you can see, iron is being poured here selectively. Now the idea of the sand around the iron is so that the iron can stay. The build powder can actually be supported, and this happens layer by layer till you have the full part. Okay. Now just the iron will not make the metal part because if you put it in a furnace, at best you're sintering it. and sintered metal without pressure, only temperature based sintering is not going to yield a strong part. So you need to have an infill. Okay, I will come to that in the video as well. The idea of the infill is once you have 3D printed this object, here iron is the build powder, sand is the support powder. This is how it actually looks inside the crucible, right? Once you have 3D printed it, you create a runner at the top of the print. Okay, a runner is like how we do it in castings or in injection molding, very similar. And that runner will be of the build powder. You can here you can see. Okay, let me pause it. The runner is of the build powder. Oh, what happened? My bad. It's pausing. Okay. Sorry for this. Okay. You see that? That runner was of the iron powder. On top of that, and you can see all the white around it was the sand. This is silica sand, very neatly deposited. On top of the runner, we place an infill metal. The infill metal is the alloying metal, alloying metal. The metal basically that is going to melt and alloy into the iron powder. And here, as you know that the iron powder is the build powder, we are using copper as the infill. So we are expecting the end alloy to be an iron copper alloy. Okay. Once this is done, you basically close a lid, you add some reducing agent into this. So reduction has to happen. So the build powder, iron powder in this case, all metals usually tend to oxidize, have an oxidized layer on their, so iron will have iron oxide on its outer boundary. And if the copper melts and drains into the from the runner into the actual print, uh, because iron is not available, iron oxide is available. Iron oxide is most these oxides are not wettable. So what we need to do is we need to remove the oxide layer. That is why we added the carbon, the coke. And what the coke does is it basically aids in reduction reaction. And I'm oversimplifying it, but basically that is the long story short. Reduction reaction is initiated, and the iron oxide layer on the iron powders are basically reduced, so that elemental iron is available for alloying and diffusion between the copper and the iron. Now I'm saying iron and copper because this example is using iron and copper. We can also print a lot of other metal alloys. Okay, as you see, the copper has melted into the iron, and basically diffusion will start taking place, and iron copper alloy will be formed. Please note that the iron never melted, only the copper was melted. So it's important that the build powder has a higher melting temperature than the infill material. The infill material is the one that is basically placed on the top. It is melted. Infilling is a very commonly used process in alloying. So there's nothing new for anyone who's well versed with alloying manufacturing. We are using the same process but in a 3D printing environment. Okay, so let's see how the part looks. Take it out of the furnace. So as you know, the copper's melting temperature is about 1080 degrees. So you have to take it above that, and you have your part. Now the video did not show the video which I earlier showed. This is not the piston part. Okay, this is a different video. Of course, we made a piston as well, and there are a lot of other objects that were made using this process. Okay, so that was the infilling way of using SPD for selective powder deposition. You can actually 3D print metals. There are two more ways you can use the machine. That is sintering. Basically, if you take the previous example, if I don't add the copper at all, okay, basically no infilling will happen. Only thing that will happen is the iron powder will actually sinter with itself. Now, some materials sinter very well, and some materials don't sinter very well. Most metals don't sinter very well. Nevertheless, it will sinter. You will have a solid object, but it will be very flaky. It will easily break and it will shrink a lot. Okay, but sometimes sintering is desirable. For example, if you want to have a very high surface area, want to create a foam, you can use sintering using metal powders itself. So that is sintering, but we use sintering for glass. I'll come later. And then the third way of using it is shell molds. So instead of the build powder being iron, if I use resin sand, I can actually just bake it or cure it at 200 degrees Celsius in an oven and have a resin sand mold. Again, I will come to that. But first, let's talk about metals. So certain parameters about the process. The powders have to be spherical between typically between 60 and 300 microns. This is not a hard rule. I'm just giving you a broad outline. Um, Now, why spherical? For flowability, because as you know, our pourer is having a 1 mm or 2 mm hole. So if you don't use spherical powders, they tend to jam and clog the pourer, and your print might suffer. But it is not a rigid requirement. Preferred to have spherical. Second is the infill metal should have a lower melting temperature than the metal powder. The third is that you must create a reducing atmosphere. So carbon monoxide or hydrogen. So if you have an atmosphere controllable furnace, you can actually work with a lot more materials than just a normal furnace, because you can actually introduce hydrogen and have very clean alloying happening. Non-reactive metals are easier to reduce. So the build powders basically it can be used are these materials: iron, copper, nickel, tin, lead, molybdenum, bismuth, cobalt, tungsten, palladium, cadmium, silver, gold, platinum are examples of non-reactive metals. They can be good choices for build powders. And for reduction reaction, anybody interested in this field, okay, I'm sure some of you might be, please refer to something as called as the Ellingham diagrams. Anybody from the metallurgy background will be well versed with it. And Ellingham diagram basically gives you what is the right amount of reduction agent to be added and what temperature will the reduction reaction take place. Finally, microstructure of this 3D printed metal alloys is quite similar to the castings. If you do casting, you will have very similar outputs. SPD does not reduce the strength in any way. Another very important aspect is there is no shrinkage in the infilling method. So there is no porosity and there is no shrinkage. No porosity if you get the process right. Okay. No shrinkage by the very characteristic of the process. Now remember, when the infill is melting and pouring through the runner, it does not interact or does not wet the support powder or the silica sand that we use. So there is no interaction. So you have to use an appropriate support powder. The molten metal should not chemically react with it, but physically it will not wet it because the refractory is not wettable in most cases. We are having shrinkage, no shrinkage, very low or negligible porosity parts. And you know what? It's a very, very low cost way to print metals. Okay. All the other ways of printing metal usually are very expensive. And in the case of sintering, if you're sintering metals, you will have significant shape distortion. It will typically shrink volumetrically, and it is excellent for printing porous glass, metals, bimetallic foams, etc. Just a quick comparison. Okay, each process has its own pro and con, but SPD has a good uh, good ranks on cost, warpage, shrinkage, porosity, and most importantly cost. Okay, because it's like 1/20th to 1/50th of other processes, or even 100. And if you're thinking that, hey, there's a furnace also required, each of these processes has a furnace required. Every metal 3D printing process, you need a furnace or you need some kind of heat treatment. So typically a very interesting way of printing metals. Now, where we are currently lacking or behind, okay, and I'm sharing this with you because you can also help us, is it's a new process. So there's a lot of good R&D or process R&D required, but from a perspective of validation, the process is very valid. Some more case studies, you can see we made a rook, which is made of brass. Then we made these tensile test specimens. These are monel or copper nickel tensile test specimen. This is actually a casting, which is also done through the mold that was shown in the first photo. So this is stainless steel casting. You can see fairly good surface finish of this casting. Now next is glass. Please bear with me. My presentation will not last for more than 5 to 7 minutes more. Um, well, for glass, we use only the sintering method and we can achieve glass objects. So far, glass has been majorly a novelty item where we have not really had any application barring some decorative use cases, some helical gears here. In fact, this is printed at Harshit Sir's lab at SVNIT. And this is a Star Wars baby Yoda that we printed using glass. we are now very close to actually start 3D printing non-porous um, and semi-transparent glass. If anybody is interested further in this area, or this is an area of work you want to explore, we can always have a discussion on this, because we are also looking for help in this field. And finally, uh, our process is now starting, our machines, this process is starting to find industrial application in an area we did not expect it to have even 1 year back. We only started off with metals and glass, but here we have shell sand molds, and now we have started to have industrial applications of this. Basically, we use resin sand as the build powder, and we use a silica or an alumina sand as a support powder. We do the SPD 3D printing. We put the crucible inside the oven or the furnace. We heat it to the about 200 degrees Celsius. The resin sand basically forms a single piece mold or a core. And then we basically melt some metal and put it into the sand mold, and we obtain the part. This is the part that we obtain through SPD printing. This was the first part, in fact. Okay, some more examples are there. Here's another video of the resin printing in action. Um, Sorry for the average video quality. The dark brown sand is the resin sand, and the white sand is the um, refractory or silica sand. This is actually for a vendor in Rajkot, in fact, and this is actually uh, one part of a butterfly valve for oil and gas applications. And this is a core for a butterfly valve castings. It's a large casting. This was a core that the company was not able to manufacture for many years. So they said, "यार हम लोग आपका try करके देखते हैं." And we were able to successfully print it for them. It's a time lapse, obviously. Uh, Takes a fair amount of time to be able to get this right. And we are also new to this process, so we are also learning, but we are actually able to, in the first try itself, have a successful 3D print. It was quite dimensionally precise as well. And yeah, so this was the video just for demonstrating the process, and some sand molds and cores. So this is the butterfly valve core that we saw in the video. This is a diffuser cup. This is an impeller mold inside an oven. It's curing. And this is just a shivling that we casted in office itself, early days. So yeah, so this is some of the things. So the machines that we are currently available in the market, sorry, it's a shameless opportunity for me to tell about us, because it is a very much research subject, so please excuse me if I'm using this platform. We are having two types of machines in the market right now. The Model C is a small machine, is the entry level machine, very capable. We are using 4 pourers, and it approximately prints about half a liter per hour volume. Then the Model G, which is an industrial level medium sized machine, it has 5 pourers. It is 4 times faster than the Model C, and it can print on a much larger build volume. And we are currently developing a large machine which will have a 1 meter by 1 meter by 1 meter build volume. This will only be for foundry customers, and hopefully in 6 months' time, they should be out in the market. Now, again, SPD versus the only other valuable method to 3D print sand molds is binder jetting. And there are only 2 or 3 companies in the world who do that. So sand 3D printing is quite new. I'm not sure many of you may have experienced sand 3D printing before. Plastics and metals, I'm sure most of you've had some exposure towards. So surprisingly, this process is 20 times cheaper in terms of machine complexity and cost than the other machines in the market, 20 times. And this is the capital expense. The operating expense for an industry is again a fraction of what the other process, the binder jetting process, costs per liter. Okay, this is like again 10% of the cost. And maintenance cost is again very low as compared to the other process. The other process, that is the binder jetting process. And for paucity of time, I did not cover the binder jetting, but if you're interested, good amount of information available online. Binder jetting for sand 3D printing. Where the binder jetting shines is that firstly, it is a evolved process, 10, 20 years old process. In fact, very interestingly, the car manufacturer BMW, all of their engine heads and sorry, engine blocks itself are manufactured using binder jetting sand molds and then casted. So it's a very, very, very well proven process. Our hope is that we also reach that level someday. The binder jetting and SPD can both give very good surface finishes, but binder jetting is slightly better. Binder jetting providers will say that buy our material, buy our binder, pay us a lot of money. Our process, we don't care. We'll give you the machine, figure it out. We also have some materials that are qualified by us, but no compulsions. There is no roller or inkjet printhead, simpler machine. And post processing is very similar, but total cost of ownership, again, it's very, very low. Final slides, 2 slides. I know I may have, no, I'm not exceeded on time. Lucky. The print time can vary between 2 hours to 100 hours. Of course, depends on the volume you're trying to print. It can even exceed 100 hours. I don't know why I've mentioned 100 only. It can be even 500 hours sometimes. Very large prints take a lot of time. Baking time depends on again the process and the furnace that you're using. And heating requirement, again, you have to have a furnace or a kiln or an oven depending on what you're using. Final slide, I think, some research areas, because I know faculty are excited to conduct research. There are a lot. This is like a very small list. A few things here are close to my heart. I one day want to be able to 3D print nitinol alloy using SPD. For that, we need an expensive furnace. If anybody has a atmosphere control furnace with them, I would really like to try this out. I believe this process is very good for making nitinol. Nobody in India makes this alloy, by the way. It's all imported. And as you know, shape memory alloy is a very, very important, it's a material of national importance, I would say. Other research areas that are part characterization, there is thermal effects of the process. Again, glass 3D printing is something that is I'm very interested in. We are trying to make transparent glasses, also colored glasses, foams. Then this is something we work on. Tungsten copper. We hope to have some work with BRC soon, because this is a radioactive shielding material. Process engineering. This is a very big area where we expect some support from R&D and academia. Some of the institutes are actually doing some good work here. It's a low-hanging fruit, lot of research scope, because it's a completely new novel additive manufacturing process, and of course foundry studies. So this is just some broad research areas of this process. And yeah, that's it. These are my credentials. If you are interested in, you can always reach out to me. This number also is available on WhatsApp. I'm available most of the times to discuss ideas and take feedback, and also discuss business if that's what you're interested in. These are the 3 things that we work on. Again, my company, the goal is that we want to make lab scale technology, advanced manufacturing lab scale technology easily affordable and accessible. So yeah, that was the presentation. Thank you so much.
Okay, thank you so much, sir. And now we opening the session for question answer. If somebody have a question, please ask.
Okay,
There is
Hitesh,
one.
yeah, Hitesh sir has a question. How
Hitesh
does
Mehta.
Hitesh Mehta sir, how does SPD improve the properties of printed metal parts? Well, so sir, firstly, uh, most of the metal 3D printing processes, there is a certain amount of porosity involved in those processes. If we get SPD correct, we achieve zero porosity parts, which is actually a really good thing, especially when you're talking about electrically conductive parts. We can actually use SPD parts. Secondly, another improvement is the shrinkage. So most there is either DED and there is laser powder bed fusion metal 3D printing systems. There is a factor of shrinkage because there is a thermal shock that happens to the part. In our process, there is no thermal shock that we are delivering to the part. There is gradual furnace heat cycling. So there is no shrinkage if you get it right again. So these are the 2 strengths of SPD. Of course, those processes have their own benefits. SPD does not have as good a surface finish as laser powder bed fusion, for example. But again, this is again subject to research to be able to say this with a lot of certainty. But I believe, from what all I've seen, SPD gives very similar part characteristics to castings, which is actually very good because castings are very widely used and very well categorized objects. So I hope I have answered your question, Hitesh sir. Dr. Amit sir, uh, thank you, sir. I would like to know how are thermal and mechanical properties holding in comparison to traditional process. Actually, Amit sir, even I would like to know that. Like I said, I can only give a little bit of information in this regard. Mechanical properties holding very good compared to traditional processes, very similar to castings. But again, we have not done extensive like fatigue testings. We have not done basic tensile testings and ISO testings have shown very good mechanical properties if the um, part is well made. And again, these will depend on different types of alloys. Some alloys will not have the same kind of compositions. So very difficult for me to give an apple to apple comparison. I believe that in the years to come, more people will adopt this process. More academia will adopt this process, do this basic and very important research and come out with more data on this. Because for us, sir, we are a very small company. It is very difficult to be able to categorize the parts and then do testing. And frankly, it is not viable financially or time wise for us. But it's a very valid question because why would somebody in the industry be interested in the parts if they are not, not validated? That is where we need help. Uh, Thank you, sir, for your question. Venkataraman, sir. Yeah, for sintering, both temperature and pressure are required. What other parameters should we consider? Well, sir, so basically you can do just temperature sintering, you can do just pressure sintering, and you can do temperature pressure sintering. If you do temperature pressure sintering in a tight mold, you can get very compact parts. So most of our carbide tools are basically sintered by just this method, where there is temperature and pressure applied inside a tight mold, and you're basically getting a very compact powder that is made into a single piece. In our case, we cannot apply pressure because, as you know, we are simply pouring the powders. If I apply pressure, it will basically deform the part. So in our case, if you're sintering, only thermal sintering is possible that I know of. If you can come up with something pressure sintering, basically the idea could be we can make a part which is already deformed in the print, and then when you apply pressure, it will actually form to its original shape. Some parts can actually do that, and then we can sinter it. Maybe that is possible, but again, it's a long shot. I cannot surely say. Dr. Alpesh Makwana, sir, is powder combination possible to create? This is a question that we always get whenever I make a presentation on the subject. Yes, it is possible. We can combine different powders to get different alloys. There is a lot of possibilities that we have. We have four pourers, remember. So two for each type of powder. There is a lot of things we can play around with. I can get into the details. We can maybe talk personally if you're interested more in that. Yeah. Any other questions? I'm happy to answer. Um, I think that's about it. Dinner time for everyone. I hope many people had uh,
Yes,
dinner
there is
already.
one hand is raised. Let me see.
Yes, sir.
We have allowed, no?
Sure.
Okay, sir. Patel. Viral. Viral Patel. Viral Bhain Ganpat Bhai Patel can ask the question now. We have allowed her. Her mic is now unmute. Is there available? Is she available? Okay, I think sir, she is not there right now. So, okay, sir.
Okay, there's another question from Venkatraman sir. This one being iron powder, why don't we apply magnetizes pressure which will not deform the shape? Sorry, sir, I didn't fully understand that. Maybe we can discuss it personally. Um, for sure. I mean, open to trying out new things, definitely. Thank you so much for
Okay.
your time and patience. I hope my talk was not very boring, and if it was, please be open with your feedback. Taylor sir, thank you so much for this opportunity. I would really like, if possible, to share all the feedback, especially the critical feedback, so that we can improve the way we discuss these things.
Sure, sir. Sure. Thank you very much to you also, sir. And
Thank
we
you,
are
sir.
looking forward for future some interaction from both way academically as well as some research point of view.
Most certainly,
So
sir.
I will invite you and we will come on the some another common platform. Now from participant, I think there is no any further query or question. So let us end this session. Let us round up close our session. And once again, thank you very much, Kalpak sir.
Thank you, sir.
Thank you. Good night to everybody.
Thank you so much for your
Thank you.
time.
Thank you, sir. Thank you very much. And but dear participant, tomorrow at 6 p.m. sharp, we will meet again. And please fill the feedback of both the session by today night itself because after 11 p.m. it will be closed. Thank you very much to all of you. Good night. Recording stop. करो.